In this section, you're going to learn to distinguish between explicit and implicit functions and be able to recognize them. You're also going to learn the implicit differentiation process, and we're going to go over several different types of notation so that you become comfortable with all of the types of notation that you have the option to use. We're going to begin with the difference between explicit and implicit functions. Explicit functions are very clear. It's very direct. For example, if I tell you that you need to do your homework or you're going to fail the class, that's very clear. You know that you're going to fail the class if you don't do your homework. However, if I tell you in order to get a good grade, you need to do your homework, it's implied that by not doing your homework, you won't get a good grade. And so that's implicit. Mathematically, we clearly state what y is equal to. Y equals something. In an implicit function, y is blended in the equation. So explicitly, y equals everything else. So we have a function f of x equals x cubed times the quantity 2x squared plus 1. That's explicit. Y equals that value. However, implicit, y is somewhere in the equation. It could show up more than once. And I may be able to solve for it, like in this one, I could solve for it, but it might become too difficult or impossible to solve for y, which is why we need an implicit form of differentiation. You're going to see me derive this particular function, 3y cubed plus x squared equals 5, a couple of different times. And each time I'm going to use an alternative notation. The first notation I chose to show to you is deriving both x and y with respect to time. The reason I chose this one first is because you need to understand that no matter what you're deriving, you're always deriving with respect to time, because as things change, time is also changing. It's passing. And so anytime we derive, we're deriving with respect to time, but we may or may not show it in our notation. So when I derive this function, I'm going to use my power rule. And so I multiply the 3 of the power times the 3 coefficient, and I get 9y squared. Because I derived y, I show delta y, the change in y, over delta t, the change in time. Plus, again, the power rule, the 2 drops in front of the x, and I get 2 to the times x to the first power, the change in x over the change in time. And then the constant 5 derives to 0. So that's deriving both y and x with respect to time. Now I want to start solving for dy dt. So I'm going to subtract my x term to the right side of the equation. So I get 9y squared dy over dt is equal to negative 2x dx over dt. And then again, solving for dy over dt, I'm going to divide negative 2x by 9y squared and multiply by dx over dt. Now I have the change in y in relation to time. And I'm going to then show you another type of notation, and this is why sometimes we don't see the notation of the change in time, because if I wanted to express this as the derivative of y with respect to x, then I would multiply by the reciprocal of dx over dt to both sides. So I would have dt over dx reciprocated times dy over dt equals 2x, negative 2x, over 9y squared. Notice that my dt's cancel, and I get dy the change in y with respect to x dx is equal to negative 2x over 9y squared. So now again, I'm going to derive this function, but this time I want to derive y with respect to x. So again, I get 9y squared. Because I touch the y, I say dy, and I just don't write the dt because I know it's going to cancel anyway. And then I get 2x, and I write dx because I derived x, and the 5 derives to 0. It gets no notation because it's constant. And then I solve for dy, just like I did in the last slide. And again, I get dy is equal to negative 2x over 9y squared dx. I divide by the dx, and I get dy over dx is equal to negative 2x over 9y squared. Just another option of how to do it. Okay? Again, we have another option. And so if I derive and I say, okay, I know it's going to come out to dy over dx anyway. So anytime I touch a y, deriving y, I get 9y squared. I'm going to go ahead and put my dy over dx. It's the change in y in relation to x. But this time, when I derive x, I'm not going to put any notation at all because I've already used it. And then that's equal to 0. And solving for dy over dx, I get 9y squared. Dy over dx is equal to negative 2x. And very simply, I can say dy over dx is equal to negative 2x over 9y squared. And I'm done. So another option. Okay, so the final notation that I'm going to show you is using y prime. The reason that this particular notation is really important, remember f prime is the same as y prime. Together, both of these are the ratio of the change in y over the change in x. The reason that the y prime notation is very popular is because when you do higher order derivatives, when you derive a second time or a third time, the y prime is an easier notation to work with. So you'll find that if you see me doing derivatives in an implicit way, you'll see me using y prime much more often than I would use any of the other notations. However, we need to be comfortable no matter what notation we use. And just a reminder, the f prime of x notation is a formal notation. We would never use that within a function. It's always a label. Okay, so again, same derivative, 9y squared, but this time because I derived y, I say y prime. Remember that blends the dy over dx, just like in the last slide. And then, so when I derive x, no notation whatsoever. And then the 5, because it's a constant, doesn't get notation, it's not a variable. There's no change in a constant. And so solving for y prime, I get 9y squared, y prime is equal to negative 2x, and y prime is equal to negative 2x over 9y squared. It's very important to notice y prime and y are two very different variables. Each of them have their own separate value, so don't blend them and don't mix them up. Okay, time to have some fun. So obviously we're going to use implicit derivation because we don't want to have to try to solve for y in this equation. And so notice in my first term, I have a product rule. Okay, so all of our old rules are going to start popping up in all of the new rules we learn. Okay, so I have a product rule in the first term. I have another product rule in the second term. And then just a simple power rule in the third term. Okay, just so that you know what I'm going to be doing. So as I do my product, I derive the x, which is 1. I don't have to write it, and I keep the y squared. Don't touch it. And because I'm deriving x, I don't put a notation. Plus, now I'm still looking at xy squared. So I keep the x, and I derive the y. I'm going to put the 2 in front of my x just to keep it clean. The y drops a power, and because I derived y, it gets a y prime label. Now I'm ready to move to the second term. So plus, and now I'm looking at the x squared, and so I derive 2x. I keep the y to the 5. Because I touched x, no notation. Plus, keep the first part, x squared, derive the y5, and I get 5, y to the 4th power, because I derived y, y prime. Now, minus my last term in the set, 3x squared, no notation because it's x, and the constant derives to 0. Okay, so it's all derived. Now it's time to solve for y prime. So I'm going to move the y squared and the 2x y to the 5th power and the negative 3x squared to the other side by either subtracting or adding the opposite of whatever I have. So I have 2x y prime staying on the left. I have 5x squared y to the 4th y prime staying on the left. Moving to the right, I have a positive 3x squared, a negative 2x y5, and a negative y squared. Okay? Notice that everything with a y prime is on the left. Y prime is common, so let's factor it out. So I get 2xy plus 5x squared y to the 4th power. That's grouped together, and I'm factoring out the y prime. Keep everything on the right just like it was. Now, on the left, this sum is multiplying the y prime, so I'm going to divide it over to the other side, and I get y prime is equal to 3x squared minus 2x y to the 5th power minus y squared over 2xy plus 5x squared y to the 4th. It's not difficult, it just will become tedious with algebra, so be careful. Don't drop negatives, make sure you're deriving right, make sure you recognize when you have a product rule or if you have a chain rule. Make sure that you're keeping track of all of the rules that you know. Okay, so you should recognize that this is a chain rule. I'm going to use my power rule on the outside, so the 3/2 is going to drop in front and subtract 1. So I drop the 3/2, I leave the inside alone. 3/2 minus 1, 1/2, and then I start deriving the inside because I have to multiply by the derivative of the inside. So derivative of x squared, 2x, derivative of y squared, 2y, but because I derived a y, I need to put y prime. Don't forget your notation. And that's equal to 0. Now notice how y prime is now trapped. So I'm going to take this entire chunk of 3/2 times the quantity x squared plus y squared to the 1/2, and I'm going to take each chunk and multiply it in. So as I multiply to the first term, notice that the 2's cancel. So I get 3 x squared plus y squared to the 1/2, nothing changes, and I have an x that's still there. So I'm going to put it up front with my 3. now I'm going to take that big chunk and I'm going to give it to the y term. So plus, again, the 2's cancel, and I have a y, so it's going to go up front with the 3, and I have my x squared plus y squared to the 1/2. And I always leave my notation in the back. So there's my y prime equals 0. Okay, now to separate anything with a y prime from everything else. So y prime's on the left, everything else to the right. So keep the 3y x squared plus y squared to the 1/2 y prime, and subtract negative 3x x squared plus y squared to the 1/2. Now notice this is multiplying my y prime, so I'm going to divide it to the other side. So I'm dividing by the 3y times x squared plus y squared to the 1/2, and I'm leaving the y prime. Notice that my x squared plus y squared to the 1/2 cancels, my 3's cancel, and this turns into this cute little y prime equals negative x over y. Who thought something so complicated could come out so simple? Okay, so our lesson wouldn't be complete without a little bit of trig. So notice we have a chain with our sign. We have a basic x, so this x is just a basic derivative, but the cosine y also a chain because it's different than 1x to the first power. And so we're going to get notation with that and have to derive that y. Okay, so start at the beginning. The derivative of sine, cosine. Remember, leave the inside angle alone. Never touch your angles. Then multiply by the derivative of the inside. So x derives to 1, no notation. Y derives to 1, but we get a notation of y prime, so 1y prime. Equals, on the right side, x derives to 1, cosine derives to negative sine. Leave the angle alone, but then remember, you need to multiply by its derivative, y prime, because it's a chain. Okay, so notice I have y primes on both sides of my equation. I need to get them together, and I need to get everything else to the other side. So again, just like before, I'm going to take this entire chunk, and I'm going to distribute it inside. So cosine of x plus y times 1, and then cosine of x plus y times y prime. And I like to protect everything from angles, so I always put that kind of stuff up front. Then on the other side, I still have 1 minus sine y, and I'm going to put my y prime up front. Okay, so now to put things on the left is going to be y prime, and then on the right, anything not y prime. So the cosine x plus y is going to subtract to the right, and the y prime sine y is going to add. So I'm adding y prime sine y, and I'm subtracting cosine x plus y. So I have, I'm going to, as I write this down, because I'm running out of space, I'm going to take my y primes out. So I have cosine x plus y plus sine y, and it's multiplying y prime. And I have 1 minus cosine x plus y. Now I'm going to divide this portion to my right side, and I get y prime is equal to 1 minus cosine x plus y, and divided by cosine x plus y plus sine y. There aren't any identities I can use to simplify that out. And so I'm just going to leave it the way it is. So for several sections now, you've been asking me why, when they give you a derivative and ask you to evaluate it at a particular x value, why are they giving you the y also? It was to get you ready for this type of problem. Because when we have implicit derivation, we can't forget that we need to plug in both the x and the y to get the actual slope at the end. So I'm taking my function xy plus x squared y squared equals 5. Remember, I've got products, so I'm going to derive first. Derivative of x is 1, and I keep the y. Plus, keep the x, derive y, which is 1, and notate it with y prime. Moving on to the second term, plus 2x, keep the y squared, plus keep the x squared, derive y squared is 2y. Notice I put my 2 up front to keep it clean, and then notate the y derivative, y prime, and then that's equal to 0. So solving for y prime, I have two terms that need to go to the other side. So I have x, y prime, plus 2x squared, y prime, staying on the left. On the right, I have negative 2x y squared minus y. And I'm going to factor out my y prime, x plus 2x squared y, quantity times y prime, and then I'm dividing. Y prime equals negative 2x y squared minus y over x plus 2x squared y. Now, all I have to do is plug in my values. So I get y prime is equal to negative 2 times 2, because that's x, y squared, 1 squared is 1, minus 1 over 2 plus 2 times 2 squared times 1. So doing a little bit of math, I get y prime is equal to negative 2 times 2, negative 4, times 1, still negative 4, minus 1, negative 5 on the top. On the bottom, I have 2 squared, which is 4. Following my order of operation, 2 times 4 is 8, times 1 is still 8. Add the 2 up front, 10. Negative 5 over 10. So simplify, y prime is equal to negative 1/2. And that would be my slope. That's my m. So if I wanted to write an equation of a tangent line, now I just use my slope and my point, and I would write my equation of my line. Okay, so you have 2 questions to do. I didn't give you really hard ones. They're pretty simple. And so I just want to see if you got the basic idea of the lesson, and then I'll be talking to you in class. Your homework is below, so please write it down and make sure you do this homework before you move on to the next lesson. Have a great day. Enjoy deriving.